Hey, Advanced Chem students, welcome to our last discussion over water and aqueous systems. This will be most of our calculations, and we'll learn about concentration of solutions, how to prep solutions, and a little bit of solution stoichiometry. So let's go ahead and get started. So solution concentration is a really important part of chemistry that we probably should have taught you a long time ago, but that's all right. Solution concentration in chemistry matters a lot. How many moles of a substance per unit of volume actually tells you a lot about how the reaction is going to occur. So you guys are familiar with concentration, whether you realize it or not. So looking at the picture here, let's say this image here is Kool-Aid. The more concentrated is going to be darker. I would say thicker, but not really. It has more particles in that certain volume. So over here on the, it's messing up on me. Over here on the right is the more concentrated, right? Concentrated. Oh, look, it's written at the bottom. Genius. And over here is the more dilute. So it even looks more dilute. But the substance that is dilute is going to have smaller amount of the solute present for that given volume, where the concentrate is going to have more of those particles per unit of volume. So there are ways to calculate this, and there are several different methods of labeling concentration or units for concentration. In biology, for instance, they use percentages. In chemistry, we use something called molarity. And molarity is the number of moles of the solute, the thing that's being dissolved, in the total liters of solution. So the solution actually includes the solute and the solvent's volume. So for instance, if you look at the examples up here, a 1 molar, that's how we say molarity, 1 molar solution is 1 mole of solute in 1 total liter of solution. So you'd have, say if it were a sodium chloride solution, like it is down here on the bottom, a 0.5 molar sodium chloride solution would have half a mole or 0.5 moles of NaCl in a liter of total solution. And it would just be written on the bottle as 0.5 capital M. This capital M, like M, is your molarity. And so we did this. We used it in our previous lab for Hess's law. You guys, Miss C and I had to show you the calculation for the number of moles from the molarity. But this is essentially what we're doing. So that was actually a 0.5 molar NaOH solution, or sodium hydroxide solution. But it would be done, kind of calculated in the same fashion. And you can use that molarity to change from liters to moles or moles to liter as a conversion factor, and we'll show you how to do that here in a bit, or I'll show you how to do that here in a bit. When you're making a solution at a certain molarity, you need to be able to prepare the solution properly. So if you know the molarity of the solution that you needed, you can calculate the number of moles and thus the number of grams, which we have over here on the left. And then you can mass on a balance the amount of grams necessary, put into what we call a volumetric flask. And I'm going to write it up here, volumetric flask. And a volumetric flask is this weird, kind of tubular looking glass. And they come in all different sizes. I've got some that are only 5 milliliters, really tiny ones. And they go all the way up to 2,000 milliliters or 2 liters for some of our larger dilutions that we do or solutions that we make. But anyway, the way that you do it is you add the mass to the volumetric flask, and then I don't think you would really use a distilled wash bottle like in the picture, but you would add distilled water until you got up to the etched line. This etched line is up here at the top. It's on the top of all of these, and that would be the registered 1 liter mark for this volumetric flask. Like I said, you can buy volumetric flasks in all kinds of sizes, 250, 100, 50 milliliters, and so forth. But this one here would be a 1 liter mark. We are going to have you guys describe how to make solutions, so you need the vocabulary that goes along with this. You'll need to describe that as a volumetric flask. So let's go try an example of this. So it says, what is the concentration and molarity of a solution made with 80 grams of sodium hydroxide in 4 liters of solution? It's really a pretty easy calculation. You just have to find the number of moles of sodium hydroxide and divide it by the volume. Remember, what we're trying to get here is our concentration, which in chemistry is molarity, and that would be the moles, which we need to solve using our grams. And then, of course, the total liters of solution in this case would be 4 liters. if I were doing this in an AP Chem class, and that's kind of what I'm going to show you guys, I would take my 80 grams of my sodium hydroxide and I would write it in dimensional analysis. But since I'm given my 4 liters of solution, I would go ahead and write 4.0 liters of solution in the denominator right away. You don't have to do it that way. You can go solve for the moles and then do a separate calculation, but sometimes students tend to early round or whatever. It's just better to do it this way. So what you're doing is setting up the density, and then you're going to change from grams of NaOH to moles of NaOH. And what you'll end up with, if we look, our grams are going to cancel. We'll be left with moles and liters. Now, 1 mole of NaOH, if I look up its molar mass, ends up being 40.0, I think. Let me double check. Yeah, 40.0 grams of sodium hydroxide. If I do that math, that's really pretty easy. It ends up being, 2 moles on top, 4 liters on the bottom. So this would end up being a 0.50 molar NaOH solution. That's how we actually calculate the concentration. But sometimes we actually, and that's fine, it's done. You could do it as 2 separate calculations, but it's completely unnecessary. Doing a simple calculation like this would actually be better. Anyway, the prettier version of it, and it's showing you the 2 different ways to do it. On top, this is doing it separately where you calculate the moles and then bring it down and then do your division. I would actually recommend doing it the way it's on the bottom like I showed you. Set up the density and then just convert the density to the molarity. You'll make fewer errors that way. Oh, look at what you did to me. But like I was trying to get in there is that we are going to ask you guys how you make a solution. So you'll actually have to describe how to do it. So here it says, how would you make 500 milliliters of 6 molar NaOH? You can't just go and measure moles on a balance. That's not possible. So what you have to do is you have to get mass. So what we need to find is the mass here that we're going to actually add to, say, a 500 milliliter volumetric flask and then add up to the etched line. So with my 6 molar NaOH, what I'm going to do is do a little bit of dimensional analysis to find out the grams. So what they've given me here is my 500 milliliters and my concentration of 6 molar. What I'm going to do is change that 500 milliliters to liters, because molarity, like we said before, the molarity capital M is the number of moles per liter. I can use that moles per liter as a conversion factor to change from liters to moles. And then I could change my moles to my grams. So what I'm going to do here is get these milliliters to liters. At that point, I could then use my molarity, which in this case was 6.00 moles of NaOH for every 1 liter of solution. At that point, I can take my moles of NaOH and change to grams. At that point, I would then have the mass. The mass here, to correct sig figs being, I guess, 3, let's see, 6.00, yeah. 3 would be 120 decimal grams of NaOH. Now, this is not what they asked for. What they asked for was, how are you going to make 500 milliliters of 6 molar? Well, now I have something that I can actually mass. I can say, okay, mass, well, I'll write it out. Mass 120 grams of sodium hydroxide, say, on a balance. Yeah, I'll go ahead and write it. There we go. On a balance. We'll say add to a 500 milliliter volumetric flask. And let's say add distilled water is labeled as DH2O. Add DH2O to the etched line. I'm not sure this is exactly what was written in the PowerPoint, but it'll certainly work. This is what I would expect my AP students to be able to write. So yeah, you can't measure moles on a balance. You can't measure molarity on a balance. So you've got to write something that you can actually do in a laboratory. So mass 120 grams of sodium hydroxide on a balance. We could have even had said solid sodium hydroxide. That would have been nice, but okay. Add to a 500 milliliter volumetric flask and add distilled water to the etched line. The PowerPoint has mass 120 grams of sodium hydroxide into volumetric flask. Add enough water to make, same thing. The etch line is where it will measure at 500 milliliters. I do wish we had one we could kind of show you today, but if you holler at us later, we'll show you one in class. They're kind of cool. Big, some of them, and cool. So another thing that this is used for, obviously, and we use this a lot in solution preparation in my classroom, are dilutions. So diluting a solution is like taking your concentrated, say, lemonade or Kool-Aid and transferring it into a more dilute solution, something you might like more. For instance, I don't really like concentrated lemonade. I really like my lemonade to be, around 25% or something. So I would take, the regular lemonade and add 75% water, and it would probably be something that I would drink. But anyway, this is the formula that we use for dilutions, and it only works for dilution. Now, I'm saying it only works for dilution, but you guys don't know the difference. We'll do some acid-base calculations later, which you'll want to use this formula, but we'll hopefully reinforce that again later and remind you that you're not supposed to. But this is like changing, say, HCl or H2SO4 to a more dilute solution of H2SO4. So it's not a chemical reaction. There's no reaction going on here. You're just taking one substance and making less of it in a certain volume, right? So you're diluting it. So I just call it M1V1, M2V2, or a dilution equation. But we'll go through and do, why don't you guys hit pause and try to do this one on your own. I'm sure you're capable. It says for a lab we need 500 milliliters of 6 molar HCl. The concentrated stuff we have in stock in the stock room is 12 molar. How are you going to make a solution using that previous formula of M1V1 equals M2V2 to solve? Hit pause, use your calculator, figure it out, and come back in a second. Okay, so let's assume you actually paused and you waited. I would list my variables like we've done in the past. I tell my students it's GFOA, given formula, work, answer. Make sure you list what your variables are. I like to make my M1 my concentrated solution, but it doesn't have to be. It could be either one. What we're trying to find out is that volume of that concentrated solution that we're actually going to use. The desired concentration here was 6 molar. And the volume that I want to have of that 6 molar is 500 milliliters. Now, normally we would change to liters when we're doing some molarity calculations, but in this particular case, we don't need to do that. Since volume is on both sides, it'll all cancel out if we do the conversion, so we can just leave it like this. It would be 12.0. Ooh, it's only 1 0. There we go. 12.0 molar. Oh, it's still the eraser. 12.0 molar. We're solving for that amount. 6.00 is our desired, times 500. Running out of room. Milliliters. And you can solve for X. Pretty easy one to start out with. You guys should have gotten about, I think it was 250 milliliters. Actually, 250 decimal would be better than 250.0. Well, let me fix that so I got my sig figs correct. Let's get rid of this right here. And let's put a decimal right there. Okay. There we go. So this is the amount that we need. The question said, how do we make this solution, or how do we make up the solution? You would need to describe how to make this. Now, there's a little bit of a hiccup here, and you guys probably don't remember this. We did it early on in our safety lab when we talked about it, but you always add acid to water. You never add water to acid. When you add water to acid, especially concentrated acid, it tends to spit and spatter, and if it's a gaseous acid like HCl, it'll actually go off as a gas. It's actually quite dangerous. So what you need to do is you add water first to the flask, and then add the acid to the water. Now, once it's diluted a little bit, you can add a little bit of water to kind of top it off, and that's the description that's here in the PowerPoint actually quite well. So it says add some distilled water first. So since you're going to make a 500 milliliter dilution, you can add, say, 200 milliliters or 225 milliliters or so of distilled water first. Then add your concentrated acid. It'll dilute. It'll actually get a little warm, exothermic, but that's okay. And then that last little 25 to 50 milliliters, go ahead and add up to the etched line, and you get your desired solution. Tricks of the trade, I'll call it, but Since we're saying it out loud, you guys do need to kind of make a note of that. It's really not wrong to go ahead and put some water in every dilution that you're doing, but it's only really necessary for concentrated acids. So like I said before, there's a few different ways to actually calculate concentration. This one is really simple, and I'm going to let you guys kind of do this calculation on your own. I'll just show you the answer. But percent solutions are often done in other areas of science or other disciplines. The example that comes to my mind is biology. Biology always calls me and asks me to make solutions for them. Oh, I need a 5% glucose solution or whatever. They're very easy to make. They're very simple. In chemistry, we seem to, you guys would probably agree, complicate things, but molarity is a much more precise way to measure these. However, we do make percent solutions occasionally, and so it's important that you guys know how to do it. Now, this is the first percent. There's a couple of different ones. There's mass volume, but this one is volume. So in volume solutions, what you do is you take the volume of the solute, the thing that you're adding, and then the total volume of the solution in the denominator. This can be done in liters. It doesn't really matter. Typically, they are done in milliliter because they're just small. But see if you guys can do this one kind of without me. So rubbing alcohol, 70% isopropyl alcohol by volume. That's what you buy at the store. How many milliliters of isopropyl are in 250 milliliter bottle of the solution? Hit pause, go ahead and give it a shot, and then come back. So again, I'm assuming that you guys hit pause and came back. Pretty easy calculation to do here. You can just set it up as a ratio. 70 over 100 is your 70%. You need a 250 milliliters of total volume, and you would get 175 had you done that math. Now, like I said, volume isn't the only way to do it. We also do a percent mass volume. This is actually more typical of what you would see in biological stuff. They'll say, oh, we need a 20%, say, glucose solution. And you would put 20 grams of glucose in 100 milliliters of solution. That would give you a 20% solution. So this one says, instead of just saying how much do you calculate, it says write directions for preparing 525 milliliters of aqueous solution containing 6.80% NaCl. So again, this is very similar to what we did before, but you got to write directions afterwards. So hit the pause button again and go and calculate how much you would need, and then write a sentence describing how you would actually make that. Go ahead and give it a shot. Okay, so assuming you did that, if you did your calculation, you could set it up the same way. You would set up saying, or setting it up as 6.80 divided by 100 equals x over 525. You find out that you need 35.7 grams of salt. I wouldn't write salt, right? NaCl, sorry. Go ahead and when you write the sentence, you're going to have to describe how to do that. So mass on a balance, whatever that mass of NaCl, 35.7 grams NaCl, go ahead and put it in a volumetric flask that is 525 milliliters. Now, they don't really make a 525 volumetric flask, but that doesn't matter. When you guys describe how to do these, you can say whatever it is that you need. It's fine. So say add to a 525 milliliter volumetric flask and fill with distilled water to the etched line. And this essentially in the PowerPoint is the same thing as I'm saying. So those are the different kinds of concentration methods of calculating concentration. Use of concentration in chemistry, we will use percents occasionally. We did it in dimensional analysis unit, and we may do it again, but only in this unit. Beyond this, you very rarely will see percents. Now, where this takes us is to something called solution stoichiometry. In solution stoichiometry, what you're doing is using that concentration as a conversion factor, which means you're using the molarity, is what we're going to use more often than percents, the molarity to change from liters to moles or moles to liters. And while this will seem really complex, it's the same thing that we did in December with stoichiometry. The only difference is that we're adding use of concentration as that conversion factor. So let's go through and do one, and then together, and then I'll give you one to go ahead and do on your own, and then I'll come back and show you what to do. So, for this first example, what volume of 0.246 molar nitric acid is required to react completely with 38.6 milliliters of 0.0515 molar barium hydroxide? So they're giving me the milliliters and the concentration, so the volume and concentration of barium hydroxide. They want me to find the volume, but they gave me the concentration of the nitric acid. What I'm going to do here is take the substance that you have two numbers for, both numbers of, and in this case barium hydroxide, and you're going to change it to the nitric acid. So what this is just straight up stoichiometry, which means a mole to mole ratio. Our ratio is going to be 1 mole of barium hydroxide from our equation to 2 moles of nitric acid. In order to get to moles, though, I'm going to have to use the one that I got both numbers for. So what I'm going to do is take my 38.6 milliliters, and I anticipate that I'm going to run out of room here. Change the milliliters to liters so I can use the molarity. Then I've got liters in the denominator here and moles on top. I can change my 0.0515 moles of the barium hydroxide to liters of barium hydroxide. Or from liters, sorry, 2 moles. I can then use my balanced equation. It is 1 mole of barium hydroxide for every 2 moles, right up at the top, of the nitric acid. Now that's just coming from my HNO3. That's coming from my mole to mole ratio. What they're asking for is the volume of the nitric acid. So what I want to do is use my molarity from there. So my molarity is the number of moles per liter, 1 liter. My moles of my nitric acid is going to be 0.246. Sorry about the small stuff, guys. Of HNO3, 1 liter HNO3. And at that point, I would kind of be done. It doesn't say how many, it says what volume. I could stop at that point, but since I had milliliters to start with, I'm going to go ahead and change this to milliliters, but it doesn't really matter. What you end up with at the end, if you do the calculation, is 16.2 milliliters of HNO3. Now, that may seem complex, but really, guys, we're doing the exact same thing we did in December. The only difference here is we're using molarity to change from moles to liters or liters to moles. We're just using molarity, or that capital M, as our conversion factor. Here is the prettier version of what I wrote. This one actually fits. But yeah, that's essentially all we're doing. So let's do one more example before we finish up. So here. So this is our last example of this unit. So calculate the number of grams of carbon dioxide that can react with 135 milliliters of a 0.357 molar solution of KOH, potassium hydroxide. And they give us a balanced equation. Notice again that they have given us two numbers associated with one of them. That's the big hint. That's what you're going to use to get to your mole to mole ratio. So, and they don't ask in this case for volume like they did the last one. They ask for the number of grams of CO2. So if they're asking for grams of CO2, can you think of what you're going to use? Go ahead and try to set this one up. Do it just like the other one. Use volume and the molarity to change to moles, mole ratio, and see if you can get this answer. So again, push pause, go give this one a shot for a few minutes, and then come back and I'll show you how to do it. Okay, so if you've gone ahead and done it, I'm going to set it up, but I'm just going to show you the work on the next one. So on the next slide. So what I'm going to do is I'm going to take my 135 milliliters like I did before. I'm going to change those milliliters to liters so that I can use my molarity, which is given up there as 0.357 moles in 1 liter. This compound, I probably should be writing the compound through all of these, is KOH. And from my balanced equation, the potassium hydroxide to get to CO2 is a 2-to-1 ratio. There are 2 moles of the KOH for every 1 mole, in this case, of the CO2. And they did not ask for volume. They asked for grams. So hopefully you guys use the molar mass, 1 mole of CO2, is 44.01 grams of CO2, and you would get your answer. Hopefully that's how you get it up. But there it is there. They used a few less sig figs in their molar mass, but that's fine. And you end up with 1.06. Not sure how you did, but fix what you need to fix. That's about as difficult as they get for solution stoichiometry for you guys. The key here, like I said before, is using the concentration as a conversion factor to convert from moles to liters or from liters to moles, and then do your mole-to-mole ratio. We won't just ask you to solve for liters and grams. We could ask you to solve for molecules. We could ask you to solve for atoms. So there may be slight hiccups in there, but essentially they're the same thing. So that concludes our unit on aqueous systems. Yeah, I guess that's it. So I'm kind of excited to be finished. So good luck, you guys. Have a great weekend, and we'll see you for the exam on Tuesday.